Suppose you have to solve a equation that has complex roots. Now, if you have to solve z to the power 4 equals to 2 plus I 2 root 3. Now, how do you solve it? The first thing to do is to take the complex number and express it as the modulus argument form. That is step 1. Let's try to do this. So this is going to be the modulus is going to be, now we're not finding the modulus of z. Remember, we are finding the modulus of the complex number that we have, which is this one. So the modulus is going to be, let me call the modulus r. It's going to be square root of 2 squared, which is x squared, plus y squared, which is 2 square root of 3 squared. That turns out to be 4 plus 4 into 3 is 12, which is square root of 16, which is 4. So that is the modulus of the complex number 2 plus I 2 root 3. Next, the argument. Now the rule for the argument is tan theta equals to y by x if x plus iy is a complex number. Let me write this down over here. If x plus iy is a complex number, then the modulus of the complex number is square root of x squared plus y squared, and the argument of the complex number, the argument is theta, so it is tan theta equals to y by x. So that's the basic rule. So it's a good idea for finding the argument if you draw it in the Argand diagram. So this is the real axis, this is the imaginary axis. So the point is x has coordinate 2 and y has coordinate 2 square root of 3. So this is the point, and the complex number is from the origin to that point. And the argument is always with the real axis. So this is the argument. It can either be 0 to pi or 0 to minus pi. So this angle we are going to find using geometry. So tan theta equals to the opposite is 2 root 3. And the adjacent is 2, which turns out to be tan inverse of square root 3, and that is 60 degree, meaning pi by 3. So that is also the argument from 0 to here, so pi by 3. So now we can write the complex number z to the power 4 as modulus cos pi by 3 plus I sine pi by 3 in that format. That is the modulus argument form. So let me write this out. So the complex number is r cos argument plus I sine argument. That is the modulus argument form of a complex number. Now the next step, we are going to try to solve this. Now how do you solve this? The first thing you do, you write z equals to 4 cos pi by 3 plus I sine pi by 3, and you have this to the power 1 by 4. This power goes to the other side. Now we can write this as 4 to the power 1 by 4 and cos pi by 3 plus I sine pi by 3 to the power 1 by 4. Now we know the de Moivre's theorem. So de Moivre's theorem. And de Moivre's theorem states that if you have cos theta plus I sine theta to the power n, it is going to be cos n theta plus I sine n theta. So now we are going to use this de Moivre's theorem and write it this 1 by 4 over here. But there is a step to it, and this is part of the presentation that we need to follow. And that is, instead of writing 1 by 4 an argument, we have to write down a revolution with the argument. Let me write this down first. So let me remove these two lines. So what we have to write over here is 4 cos. Now instead of only pi by 3, we have to write pi by 3 plus revolution, which is 2 pi k, plus I sine argument pi by 3 plus revolution 2 pi k, and then we are going to give the whole thing as to the power 1 by 4. That is the step we have to write. Now why do we have to write this with the argument plus 2 pi k? You see, what happens is that we have arbitrary angle. Suppose this is an arbitrary angle theta. So from the revolution, as we keep moving on, we'll get many angles of different arbitrary angle as we move on and on and on through the revolution. So the 2 pi represents one revolution, and k means how many times you're moving on. You can have k equals to 1, meaning 1 revolution. You can have k equals to 2, meaning 2 revolution. You can have k equals to 3, meaning 1, 2, 3 revolution, or you can have minus 1 revolution. That means in the opposite direction. You can have minus 2 twice in the opposite direction, that sort of thing, because it's like solving arbitrary angles. So remember, the first step is to write down it as revolution. So argument plus 2 pi k, argument plus 2 pi k. Okay, let's get going. So 4 to the power 1 by 4. Now this is going to be De Moivre's theorem, so the power is going to be a coefficient. So it would be cos 1 by 4 pi by 3 plus 2 pi k plus I sine 1 by 4 pi by 3 plus 2 pi k, and that's it. Now we have to simplify this. So 4 to the power 1 by 4 is 2 square multiplied by 1 by 4. And if you multiply, this is going to be 1 by 4 into pi by 3 is pi by 12 plus 1 by 2 pi k plus I sine 1 by 4, this is pi by 12 plus 1 by 2 pi k. So we have this. So 2 to the power half is square root 2, and this is going to be cos pi by 12 plus half pi k plus I sine pi by 12 plus half pi k, and now we have to find the root. Now what we have to do, we have to take values of k as 0, meaning the first revolution, 1 meaning after one complete revolution, 2 meaning 2 complete revolutions, and we see whether that is a root or not. Now how do you know that? You see, we have to make sure that the argument is either 0 to pi or 0 to minus pi. That's all that we have to do. Either 0 to pi or 0 to minus pi. That's what we have to do. If the argument is more than 0 to pi or less than 0 to minus pi, we cannot take that value. So the trick is, just check if the coefficient of pi, whether it is positive or negative, that doesn't matter, whether the coefficient of pi is less than 1. How do you know that? If the denominator, meaning downstairs, is greater than the upstairs, then it would be less than 1. So let's continue. For k equals to 0, z equals to square root of 2 cos 0, this portion is 0, pi by 12 plus I sine pi by 12. So as we can see, the coefficient of pi 1 by 12 is less than 1. That means it is within 0 to pi. So this is an acceptable root of this equation. Now let's take k equals to 1. So z equals to square root of 2 cos. Now if we put k equals to 1, it becomes pi by 12 plus half pi. So let's check with the calculator what that turns out to be. So pi by 12 means 1 by 12. Then we have plus, and we have half pi, which is half, and that turns out to be 7 by 12. So 7 pi by 12, it is also less than 1. So 7 by 12 pi plus I, this one will also be the same, 7 by 12 pi. So as you can see, the coefficient of pi upstairs is less than 1, upstairs is less than the denominator downstairs. So 7 by 12, the whole coefficient is less than 1, that means it is within 0 to pi. Now let's take k equals to 2. If we take k equals to 2, what would happen? It would be pi by 12 plus 2 into half is pi. So it is already greater than pi. So it would be pi plus pi by 12. So we know beforehand that this is going to be more than pi. So we don't have to take k equals to 2. So let's take k equals to minus 1. For k equals to minus 1. If we take k equals to minus 1 over here, so what would happen? We will have pi by 12 minus half pi. So let's check what that turns out to be. So pi by 12 meaning 1 by 12 minus half pi meaning half. So it is minus pi by 12. So this would be. So when we put the value of k equals to minus 1, we get minus 5 pi by 12. So z equals to square root of 2 cos minus 5 pi by 12 plus I sine minus 5 pi by 12. Now k equals to 2 didn't work, but k equals to minus 2 might work. So let's check. If we put k equals to minus 2, it turns out to be pi by 12 minus pi. So pi by 12 minus pi, let's check what that turns out to be. So 1 by 12 minus 1, and that is minus 11 by 12, which is also less than 1. So minus 11 by 12. So we have for k equals to minus 2, z equals to square root of 2 cos minus 11 pi by 12 plus I sine minus 11 pi by 12. And these are the 4 roots of the equation z to the power 4 equals to 2 plus I 2 square root of 3.